Neutrinos are interesting because they are so small, they will fly through almost anything. There are trillions of them flying through a person every second, but most of these are the lower energy neutrinos than the ones that we were looking at. And almost none of them will interact with the human body.
Up until now, for any other neutrino experiment that has come before, you could safely assume that neutrinos will pass through anything on their way to a detector.
So what IceCube brings to the table, the first time we can actually see the beam of neutrinos being stopped in the Earth.
And that's a very interesting particle physics measurement at huge energies where we have no neutrino beams on Earth to do the same experiment.
So in interaction cross-section, it can be thought of as the probability for a neutrino to interact with an individual proton or atomic nucleus. Then if you put that up into an aggregate like the Earth, it's a measure of the neutrino's penetrating ability.
But the more energy a neutrino has, the more likely it is to interact with the nucleus. And eventually, you would expect that if you have a high enough energy neutrino, the entire Earth could stop it.
For the first time, IceCube has measured the absorption of these high-energy neutrinos in the Earth. The splinters for a neutrino-to-nucleon interaction include a particle called a muon. When comparing the number of muons detected from the horizon to the number of muons that are coming straight up through the core, we can see that many of the neutrinos are disappearing if they had to come through the dense Earth.
What we did is we measured the arrival angle of the neutrino and the energy deposit at the detector.
Our measurement is valid between about 6 TeV and 980 TeV, which is over 2,000 times higher energy than the previous accelerator measurements.
Eventually, we got our data support the standard cross-section.
So once more the standard model, triumphs, as it does all the time.
The standard model doesn't get everything perfectly right when it comes to particle behavior. Some theorists are trying to reconcile the problem and have come up with ideas that modify the standard model.
We know that the standard model cannot be true forever, and that's specifically the case for neutrinos. It's very specific, because we discovered that neutrinos have mass, and that's inconsistent with the standard model. And specifically in this case, there were ideas that the universe has more than 4 dimensions. Unfortunately, it's very hard to calculate exactly at what rate or at what speed or how soon these dimensions appear. And so we learned that we are not there yet, or that they just don't exist, and that the world is made of 4 dimensions.
The existing measurement used 1 year of IceCube data. We already have 7 years of data on tape. So clearly we want to do an improved analysis with all 7 years of data to see more and more detail how the cross-section rises with energy.
We know pretty well how many nucleons there are in the Earth, even though the planet has different densities in the core, the mantle, and the crust.
If our measurement proves, okay, the standard model is correct for the neutrino cross-section, then we can start using this cross-section to measure the Earth itself.
We can actually measure not just the density of the core, but the composition. Exactly what material makes up the core.
The geophysics world is really interested in, we have a new tool to peek inside the deep in Earth.
So in the near term, we'd like to build something called IceCube Gen 2, which would be 10 times larger than IceCube and let us study neutrino interaction to higher energies and really be sensitive to new physics sort of beyond the standard model.
Studies like this help physicists to understand the world of particle physics and to better explain why things happen. This may lead to better energy production on Earth, or maybe different methods of space travel.